Hi everyone, in this video we're talking about section 3.2 from your textbook, which is about measures of dispersion for a data set. Specifically, we're going to be talking about what we mean by dispersion and some different ways to again measure it or quantify dispersion, which are going to be range, variance, and standard deviation. So we're continuing on with the theme of descriptive statistics. You might say that range, variance, and standard deviation are all statistics that describe data sets. So just like in section 3.1, and actually for all of chapter 3, we're doing descriptive statistics. Now dispersion just refers to how much a data set is spread out. And so what I have here to show you is two data sets, which we'll call A and B. And each blue dot is going to represent one measurement in the data set. So we might name this measurement like X subscript 1, and this measurement like Y subscript 1. And there's about 30 dots. There's about 30 blue dots in each data set. And what I want to point out though is that I would say that the B data set seems to be more spread out than the first data set, right? So actually both of these data sets have the same mean. The sample mean of each of these is actually 0. So that's where they're centered around, mean being a measure of central tendency. However, again, the B data set seems to be more spread out, so we would say it has more dispersion. Range is just a way to quantify dispersion. So rather than just saying qualitatively, B looks like it's more dispersed than my A data set, we can actually put a number to it. And the way we're going to do this is we're going to say that range is equal to max minus minimum. So my range for my data set A is going to just be its maximum value minus the minimum value, which is going to be something like 1.9 minus negative 2.1. So this difference here between the max and the min, this is my range, which is just max minus min. Okay. And this is like 4. So this first A data set has a range of 4. And then what about my B data set? What would be the range of data set B? Well, again, max minus min tells me this is something like 4.6 minus negative 3.9. So the data set B has a range of about 8.5. So taking the difference between the maximum and the minimum values, it's about 8.5. So we can say that B appears to be more dispersed, and it also has a larger range. The range is like twice as much for the B data set. And so that's how range is telling you which data set is more dispersed. However, let's consider another data set. So this time we're comparing data set B with data set C. And these two data sets have the same sample mean. So the sample mean here is right at 0. And they actually have the same maximum values and the same minimum values. But just taking a look at these and where those blue dots are that represent each measurement, would you say that C or B have the same dispersion or different dispersions? Is one of them more dispersed than the other? And just me personally, I would still think that the measurements in B are more spread out than the measurements in C overall, because in the measurements in C, most of them fall here. And of course we have some outliers, but for data set B, the measurements seem to be more spread out over a larger range. So even though these technically have the same range, right? Because if you have the same maximum and you have the same minimum, that means you have the same range of the data set. And so I would still say that they have different degrees of dispersion despite having the same range. So what I mean to point out here with this slide is that range is just one of the toolkits we use to quantify dispersion, but it's not the best tool in our toolkit. And we're about to introduce some other measures of dispersion that are a little bit better suited towards differentiating in this scenario. And before we start, as kind of an introduction, I want to explain what we call deviations. So whenever you see the word deviation, it's this difference right here. This is what I mean by a deviation. And so x with subscript I, remember that's just some measurement, so we might call this one x subscript 1. And then x bar is just the mean, the sample mean. So for these data sets, again I named them B and C. The sample mean is right here at 0. And the deviation here would be the difference between any one of these measurements and the mean. So this would be like x1 minus x bar. And if I really was concerned about this measurement right here, which is maybe like x subscript like 12 or something like that, and I wanted to calculate the deviation here, I'd do x12 minus the sample mean. But, we're talking about the deviation of each point in the data set. And if the data is more dispersed, we would think that each data point is going to tend to have a larger deviation when we consider all of the data points. And so maybe you think a good measurement would be to just add up all of the deviations for all of the measurements. However, I can tell you that adding up the deviations always gives you a sum of 0. And I want to tell you why this happens and why that obviously is not going to work if it always gives you 0. But I'll need some space to do this, and we're going to imagine just a smaller data set to wrap our minds around this. But suppose I have a data set with 3 measurements, which I name x1, x2, and x3. Then my sample mean, I'll use x bar for the sample mean. I'm going to calculate that by adding these up, x1 plus x2 plus x3, and then dividing by the number of measurements, so I divide by 3. And if I were just going to add up the deviations for all 3 of these data points, what would that look like? Well, that would look like the first deviation, x1 minus x bar, plus the second deviation, x2 minus x bar, plus the third deviation, which is x3 minus x bar. And this would just be the sum. That's just adding together all the deviations. But let's remove the parentheses for a moment. And so removing the parentheses, because I'm allowed to do that, addition and subtraction. Well, addition anyways is commutative, and subtraction, as long as we just consider those to be negative x bars and we're adding them, then we can move those around as we want. And so if I get rid of the parentheses, which you remember we're allowed to do from algebra class, what I get is this right here. And I'm going to collect all of my negative x bars. So I have x1 plus x2 plus x3 minus 3 times x bar. And now I'm going to replace x bar with this definition that I gave for x bar. So I have x1 plus x2 plus x3 minus 3 times x1 plus x2 plus x3 divided by 3. So this 3 in the numerator is now going to cancel with that 3 in the denominator. And then this negative sign out front is going to distribute to each of those x's. And so what we'll end up with is x1 plus x2 plus x3 minus x1, because I distribute that negative, minus x2, because I distribute this negative, and then minus x3, because I distribute that negative, and of course these all cancel out to 0. And so if you actually calculate your mean properly, your sample mean properly, and you were to conduct this sum of all of the deviations, it's going to give you 0, and you can try it for other sample sizes or for an arbitrary sample size, and you can always find that these are going to cancel out just necessarily. So what we want to do is we want to consider the deviation of each point. But we found out that adding all those up is not going to work. So we really have two options that seem reasonable to me at the moment. The two options that I would tell you to consider are to add up all of the absolute values of the deviations, because if you take the absolute value of each one, then they're all positive, and if you add up a bunch of positive numbers, well, that has to be a positive number, it can't be 0. And so that seems pretty logical. Or we could square those deviations and add them all up. Again, when you square a negative number, it gives you a positive number. And so adding up each of those terms would also give you a positive number, and it could never be 0. And so I'm thinking that either one you choose is pretty reasonable. We just have to decide. And we're going to select this one. And I can definitely see arguments for why the first one might seem more intuitive, but I want to present to you a short argument about why the second choice is the choice we typically use. I think I introduced this in the last video. So if I show you capital SST, this stands for the sum of squares total, and we use this acronym to represent exactly what we're talking about, which is adding up all of the squared deviations. And this is actually a good measurement of dispersion if you're only comparing data sets with the same number of measurements. But notice if you have one data set that has 10 measurements, let's call this data set D and data set E. If you have one data set with 10 measurements, and you have one other data set with 30 measurements, and you wanted to compare the dispersion between these two, well, naturally, any data set with more measurements is going to have more of these terms in your summation, and so of course, the sum of squared deviations, or the SST, is going to be greater whenever you have more measurements. In other words, the more measurements you make, the larger the SST value becomes. And so if you fail to account for this, I say SST is a bad measure of dispersion because you may want to compare the dispersion of two data sets that have a different number of measurements. And you don't want the larger sample size to automatically get, a penalty for just having a large number of measurements. So we're going to adjust for this. We are going to just divide by n. And if I divide that sum of squared deviations by the number of measurements, basically what it's telling you is, we're taking the average of the squared deviations. So now even if you have more measurements, it's not going to be a penalty towards the data sets that have more measurements, because we're actually also going to divide by the number of measurements. And so if n becomes larger, your denominator becomes larger, and this total, this value here, is going to become smaller when the denominator becomes larger for the same numerator. So anyways, this actually, this checks out. This is a much better way than just sum of squared deviations alone if you're trying to compare the deviation between data sets with different numbers of measurements. And let's talk about now something that we actually use in the practice of statistics. We're talking about variance. And the formula for sample variance is given here. The formula for sample variance is this. The sum of the squared deviations on top, and on the bottom we have n minus 1. Remember that capital Greek letter sigma means sum, and we're summing over all of the deviations squared for each of the measurements. And notice that this is the symbol for sample variance. So if I'm talking about sample variance, I'm going to use a lowercase s squared. Not just lowercase s by itself, but it's going to be lowercase f squared is the symbol for sample variance. Okay. Now, when it comes to variance, we see population variance, which is a parameter, and sample variance, which is a statistic. And you'll notice the difference between these formulas is that we use mu, the population mean, we use a sigma squared to represent population variance, and for sample variance we use s squared to talk about the sample variance, and we use x bar to talk about the sample mean. And also one more thing, if you're really keen, is that the sample variance does use that n-1 in the denominator, whereas if you are talking about an entire population, you actually only use n in the denominator. For our purposes in this class, we will always calculate the sample variance, and so we always need an n-1 in the denominator. So for variance, why the numerator? The numerator is the sum of squared deviations, and so that quantifies how far each point is away from the mean. By squaring those deviations, that means if you have a large deviation, it becomes even larger, and if you have a small deviation, it becomes even smaller before you're adding them up. So remember what the function looks like when you graph it for the x squared function. Is if you have something really small, it actually squishes it down, and if you have something really large, it actually makes it larger, because this graph goes from being very shallow around x equals 0 to being really steep as x gets larger. And so this penalizes big deviations even more than small deviations. And that's kind of something that you want if you're looking for a measurement of dispersion. And also, remember, the mean is the point that solves a particular optimization problem. The mean is the point that actually minimizes the sum of squared deviations. And the mean was important to us because it represents the expected value of a random process. And in any case, this sort of has a certain relationship to the mean. The variance and the mean are related. And since we care so much about the mean, it's natural that we should also care about this variance, or about this SST. Also, on the bottom I put, remember, the mean does not minimize the sum of absolute distances, it minimizes SST, which is the sum of squared deviations. Actually, the median is what minimizes the sum of the absolute distances. Okay, so sample variance. Why the denominator? And we divide by n so that a sample is not penalized for having more individuals. We talked about that. What about the -1? Well, n-1 is also called the degrees of freedom, and you'll see at the end of this video I will do a quick demonstration using Microsoft Excel, and we'll simulate a random process. And you'll see that this formula for the sample variance is actually better at, put an extra a on the end there, this formula for the sample variance is better at approximating the parameter we're trying to approximate. So this is better at approximating the population variance, where the population variance is a parameter. Remember, parameters are characteristics of populations that we can never really know, but this formula is better at approximating the population variance than if you were to just take the average of the squared deviations. So that's why we use n-1 in the denominator. It just makes this into a better statistic. Finally, we're talking about standard deviation, and I want to tell you standard deviation is just the square root of the variance. Please remember this. You must remember this for any exam that you're going to take in this course. The standard deviation, it's just the square root of the variance, which means that the variance is just standard deviation squared. And this actually comes up in the way that we use our notation, because for variance, we use the symbol s squared, And for standard deviation, we use the symbol S. So just in the very symbol we use itself, you can see how the relationship is between standard deviation and variance. So for population standard deviation, we just use sigma. Remember, population variance was sigma squared. So for population standard deviation, which is just the square root of the variance, the square root of population variance, then this is, again, the same formula for population variance, just with the big square root radical around it. And then the same thing for the sample standard deviation. Again, we just use lowercase s, because the sample standard deviation is the square root of the variance. And this is, again, the same formula we had before for the sample variance, but now just with a square root radical around it. So why would we bother talking about standard deviation? If variance is already a good measure of the dispersion of a data set, why would we bother calculating standard deviation? Well, so we're going to illustrate this by calculating the variance for this sample of lizard lengths. And so to do this, we first need to know the mean, the sample mean. Sample mean being x bar, that will be 15 plus 13 plus 18 plus 14. And just, trying to sum these up, 15 plus 13 will be 28. 18 plus 14 is going to be 32. Oops. Sorry, I don't know what I'm doing here. A little sleepy today. That'll be 28 plus 32, which is 60. And there's 4 measurements, so we divide by 4. And so this would be 15. It's our sample mean. So our sample mean is 15. We're going to calculate the deviation for each of these. So if this is our data set, our deviations here are going to be 15 minus the mean. 15 minus 15 is 0. 13 minus 15 would be negative 2. 18 minus 15 is 3, and 14 minus 15 is negative 1. So this is a set of deviations that correspond to my measurements in this data set. I want to square the deviations, and so 0 squared is still 0. Negative 2 squared is 4, 3 squared is 9, negative 1 squared is 1. And then the sum of squared deviations, which we call SST, would just be 4 plus 9 plus 1, which is 14. Remember, sample variance, we use lowercase s squared to represent sample variance, and this is just the SST divided by the n minus 1. So this is going to be 14 over 3, and we get 14 thirds, which is like a little bit less than 5. It's like 4 2/3. Okay. Let's talk about something that happens in real life. In real life, whenever you are, taking measurements, you always take measurements with what we call units of measure. Measurements always come with units of measure. And in this case, when we measured the lengths of these lizards, the unit of measurement we used was centimeters. So this lizard was 15 centimeters long, for example. Let's see what happens to our unit of measurement as we carry it through this whole process. So our mean, our sample mean, the mean lizard length would be 15 centimeters because we're adding up measurements which are made in centimeters. And so this would be 60 centimeters divided by 4 lizards gives me 15 centimeters for the sample mean. When we calculated these deviations, we were taking measurements in terms of centimeters and subtracting the sample mean in terms of centimeters. And so a difference between two lengths in centimeters, well, the difference between lengths in centimeters is also in centimeters. When we squared those deviations, whenever you square a length, you get an area, and so squaring a length in centimeters gives you an area in centimeters squared. When we summed up those areas in centimeters squared, I got a sum of squared deviations, which was in centimeters squared from a unit of measurement. And then we went to calculate our sample variance, which was just the SST divided by n minus 1. And so our 14 as our sum of squared deviations was in 14 centimeters squared. And we divide that by 3, which is just 4 measurements minus 1 measurement is 3. Our sample variance is in units of centimeters squared. So we have measurements in centimeters and a sample variance in centimeters squared. And basically the reason why we chose, all statisticians seem to find it more comforting or more familiar to talk about dispersion in terms of standard deviation. The reason is because whenever you go ahead and take the square root of the variance, this actually gives you a number for standard deviation in terms of centimeters instead of centimeters squared. So you're talking about the dispersion of lizard tails, the dispersion of the length of a lizard. You want that measure of dispersion to also have units of length. And so whenever we actually take the square root of our sample variance, it'll be 2.16. So we say the standard deviation of the length of a lizard tail, or sample standard deviation, will be 2.16 centimeters. And hopefully it makes more sense to you that if your measurements are in centimeters, you want measures of dispersion that are also in centimeters. So this is the purpose of the sample standard deviation. So anyways, standard deviation is a way to put your measure of dispersion back in terms of the original unit of measurement for your data set. Maybe many of you said, why is there an n minus 1 in the denominator, right? Like, this doesn't really make a whole lot of sense why we would subtract 1 from the denominator. We just went through this discussion about how you could take the sum of squared deviations as a measure of dispersion, but then to compare data sets with different numbers of measurements, maybe you want to divide by the number of measurements, and that seemed fair to us because it was the average of the squared deviations for a particular data set. But then when I introduced variance, you noticed, hey, there's an n minus 1 in the denominator instead of n. And there's a good reason for this. And I want to demonstrate to you why using a little simulation that I created in Excel. So we'll pause for a second. So here we are in a brand new workbook in Microsoft Excel. And what I want to do is a little simulation. So if you want to simulate a normal probability distribution in Excel, first you have to decide on what your parameters are going to be. And so one parameter you will choose is the population mean and the population standard deviation. And also we will, just for the heck of it, calculate the population variance. And so for population mean, let's just choose 50. For population standard deviation, we'll choose 10. And for population variance, I want to point out that variance is always just the square of the standard deviation. I'll say that probably many more times during this video. And so we've chosen these parameters, and in real life, I want to point out that you probably won't ever be able to know these parameters, right? We typically never can figure out parameters, and we just estimate parameters using statistics. But in a simulation, you actually choose the parameters. So in this particular simulation, we're going to choose these parameters. What I need next is I'm going to calculate sample mean, I'm going to calculate RSS, I'm going to calculate obviously sample size, variance using n in the denominator, and then I'm also going to calculate variance using n minus 1 in the denominator. Not n times n minus 1, that's a typo. And of course we're talking about sample variance. Ooh, there we go. All right, and so what we're going to do is we're going to generate some random numbers. We're going to calculate the sample variance using these two different methods, two different formulas, one using n in the denominator, one using n minus 1. And then we're going to compare that to the population variance that we chose for our simulation and see which one is closer. All right, so for my simulation, I'm going to take 10 measurements. So M1, M2, M3. Actually, we typically have been using in this lecture X for measurements. So for our data, we'll label X1, X2, X3, X4, X5, X6, 7, 8, 9, and X10. I need to calculate the deviations for each of these two. So I'm going to use the letter D to represent deviation. So I've got D1, D2, D3, and so on. Maybe Excel is going to make my life easier. There we go. So I have 10 deviations that I'll calculate. And then I want to figure out what are these deviations squared. Remember, I have to square each of the deviations. And doing that, I'll get 10 terms of squared deviations. And then to get the sum, the SST, or the sum of squared deviations, I just have to add those up. And then, actually, I think I put a line for SST way up here. Yeah. SST, that's what I meant. So here we go. RSS is something different we're going to learn about next week in chapter 4. All right, so with this simulation, let's first generate some random measurements. And the way you do this in Excel is you select the cell where you want your random measurement to be placed. Type equals norm.inv, open parentheses, RAND. And so the RAND part is creating our random number between 0 and 1. And the norm.inv formula is what's going to create us normally distributed random data. With a mean, which is our population mean, and a standard deviation, which is our population standard deviation. And here we go. Random number, drag it down. So we have more random numbers, but if you're really keen with Excel, you can see my mistake. I actually want to lock the row 2 and row 3 in place for cell references. So having done that, it's fixed. Deviations now. Well, for a deviation, I first need to calculate the sample mean, and the sample mean is just the average of these measurements. The SST, we're going to calculate that later. N will be 10. Of course, I've generated 10 measurements. And now we can calculate deviations, right? So the deviation is nothing but the measurement minus the mean, or the sample mean. And I'm going to lock the row reference, the B6. I'm going to lock that in place with a $sign. So that way the row won't change when I drag this down. So this deviation 10 will be measurement 10 minus sample mean. Okay, and when I want to square these, I will just do equals, reference one of those deviations, and then caret 2 to square it. And I have 10 different squared deviations. For SST, remember that's the sum of all the squared deviations. So I type equals sum, open parentheses, and I'm going to select all the squared deviations, close parentheses, and I have an SST value calculated. And now what would be the sample variance? The sample variance is going to be the SST divided by n for this particular one, because I want to try out what would it be like if I used just n in the denominator. This would be like the average squared deviation for our data set. And then we're going to try the same thing again. We're going to calculate variance using n minus 1 in the denominator. So I type n minus 1 down here. Oh, except instead of n, we actually need to reference what is my value for n. So I have 10 measurements, n is 10. Okay. And so what I've done is I've actually created a little simulation. And the trick to this simulation that's going to make it worthwhile for us is to do this over and over and over many times. And I want to keep using the same mean and the same standard deviation to create this random data. So to lock the B column in place, I'll also use $signs. And I'm just going to press F9 over and over and over again. And I want to show you, just look at the sample variance using n-1, and look at the sample variance using n, and ask yourself which of these values is actually closer to the population variance. And so what we want is we want our statistic to be a good estimate of the parameter. So these being different ways we could calculate our statistic, which is the sample variance. Sample variance is a statistic. And then this population variance is a parameter. So we want these numbers to be good estimates of this number. We want the one that's closer to 100. Okay? So right now already n-1 is closer. The sample variance formula using n-1 in the denominator is closer to the population variance. But it's not very close. Okay, so in Excel, if you press F9, it will recalculate the worksheet. And for us, that means it's going to choose new random numbers from the same distribution. So every time I press F9, we're going to get new numbers for the sample variance, for example. And these are going to, of course, change each time. And so sometimes the one formula will be better, and sometimes the other formula will be better. Like in this case, you would have a solid argument for using n in the denominator instead of n-1 because it's closer to the parameter you're trying to estimate. But to get a good feel for which one is really better, what we need to do is just simulate this a whole bunch of times, like a lot. And so what I'm going to do is I'm going to select this whole column B, and I'm going to use the bottom right corner to drag it out to the right. Now, if I use n-1 in the denominator, the average of all those sample statistics was 101.19. If I used n in the denominator, of course it's less, so it's 91. And let me just continue to press F9 a few more times to sort of restart all 1,000 plus simulations. And whenever I do a large number of simulations and I average together the sample variance that we calculate, it seems like the formula using n-1 in the denominator is really better than the formula where I only use n in the denominator. As far as being a good estimate of the parameter we're trying to estimate again is the population variance. Okay.